Today, I will be discussing the quantization of GPT-2 using SmoothQuant. To introduce this topic, I want to talk about the importance of quantization for LLMs. Today, more than ever, LLMs are growing rapidly. GPT-4, one of the more popular models, is 1.76 trillion parameters. This means that the gap between model size and GPU memory is only growing. Therefore, we have to research ways of try and reduce the model size. Today, we will look at one of such techniques called quantization. And this specific quantization technique was developed by MIT Ham Labs that quantizes the parameters from FP16 to int8. We will demonstrate this technology on GPT-2, part of the GPT family, which is popular and relevant today. Here is a brief visualization of the parameter sizes. Most models use FP32 or FP16, but clearly we see that int8 is much smaller than that, helping to reduce the model size by a factor of almost 4 from FP32. To show how quantization works, here's a slide of the equation of it. Basically, what you do here is you get the max element of each tensor and divide it by 2 to the n minus 1 bits minus 1. Then you take that factor and divide each element of the tensor by that factor and take either the floor or the ceiling of it, as you can see here. I wanted to mention more about the model that I used for this demonstration. It's the GPT-2 model, and I had various options. But for this project, considering the timing constraints, I decided to use only the GPT-2 small and the GPT-2 very large models to see whether there's difference between quantizing bigger and smaller models. Additionally, there was variety of GPT-2 models for different purposes. However, for this one, I chose the one that's best used for text generation as it's easiest to evaluate. And it's called the GPT-2 LM head model. So how were the models evaluated? The models were evaluated on the perplexity benchmark. And this benchmark basically measures the confidence the model has in its next prediction. Mathematically, it's the exponentiated average of the negative log likelihoods of the sequence, as we can see here. The perplexity was measured on the raw second version of the Wikitext dataset to align with the research paper and to better compare the results that we got. To ensure that the evaluation was correct, I tested it on the smallest GPT-2 model that has 124 parameters and calculated that the perplexity was 29.93, while the perplexity calculated in the original paper for GPT-2 published by OpenAI was 29.41. Similarly, for the largest GPT-2 model, I calculated the perplexity as 17.40, while the perplexity calculated in the original paper was 18.34. Although not completely exact, it showed that the perplexity calculations were approximately correct and that we could proceed to the next steps. Although quantization is a promising technique in large language models, and although it is used commonly for neural networks, and technically LLMs are based on neural networks, there's still a big challenge in quantization. And that is the fact that activations have much larger outliers than the weights in models. And that was also the case for our GPT-2 model. As we can see in the graphs, the mean of the activations for one of the multi-layer perceptrons was 0.95, while one of the outliers was almost 10 units. On the other hand, for the weight parameters, the mean was 0.51, but the maximum outlier was 121. And these outliers are a challenge for quantization because they skew the scale factor, which may cause information loss and also increases perplexity as follows. So what is SmoothQuant and how does it work? SmoothQuant is a quantization technique that aims to resolve the problem of outliers. And it does this by transferring the outliers to the weights. And here's a pretty simple example that's easy to visualize and comprehend. X here stands for the activation tensor, and we take the absolute max value of each column of it. So here we have, for example, 1 minus 2, and then we take the 2 out of here. For the weight tensor, we take the maximum of each row. So, for example, here we have 2, 1 minus 2, and we get the 2. Then we divide the absolute value max scale that we got from the activation by the weight, and then later multiply that scale we got by the whole, use it to multiply the whole weight matrix. However, using this method, we're basically transferring all the outliers from the activation to the weights, which is not always what we want to do, especially if the outliers are not as impactful. Therefore, the paper introduced a parameter called alpha, which basically tells us how much of those outliers we want to transfer. And it's a hyperparameter that we can experiment with. Next, I wanted to talk more about the flow of how I applied SmoothQuant. So first of all, I had to create custom weight 8 activation 8 linear layers from the linear layers of the model. And one of the challenges I had there is that compared to Llama and OPT and Bloom models that SmoothQuant was originally written for, GPT-2 doesn't use GPT-2 uses one-dimensional convolutional layers that are part of the transformers library. And so they had a bit different notation. So they had a need of creating custom linear layers for them. And then after creating those linear layers, I quantized them per channel for the weight quants and per tokens for the activation quants. After that, we had to get the activation scales for the linear layers. In this case, I used 520 random samples from the pile dataset. And the pile dataset is a dataset compiled from various sources like Wikipedia articles and even YouTube subtitles. Recently, it has been copyrighted. However, I found an uncopyrighted version of it and used that. The third step was to get the max absolute value of each column of the activation scales. Next, we got the max absolute value of each row in the weight scales. And finally, we calculated the scaling factor based on the weight and activation scales and the alpha factor. Here, alpha is the parameter that says how much of the outliers will be transferred from activations to weights, as I explained previously. The only thing that was left to do was quantizing the model using this scale factor by multiplying it by the weight parameters. In the end, we evaluated the model using the perplexity benchmark and the Wikitext dataset. Once again, due to the differences in architecture between GPT-2 and Llama, I had to try 3 different methods of application of SmoothQuant on this model. So the first method was the most similar one to the original method that was used for Llama. Here, I took two of each layers, attention and MLP, and got the max of each end columns to reduce the input size of the second layers. because in the llama layers, the dimensions, the in channels and the out channels were the same. However, in this case, the dimensions were different. And so I had to somehow reduce the in channel dimension. Then, like in the original implementation, I concatenated the two tensors and took the max of each row and used that to calculate the factor S. I also used that factor to divide the normalization layer by that factor to ensure that we are feeding in the scaled parameters. The next two methods I tried was instead of getting the max of each of the getting the max of the concatenated activation layers, I quantized each linear layer by using its own activations. And in the final method, I only quantized the layer with the biggest outlier using its activation parameters. And here were the results. Although I wasn't able to get the original perplexity of the model due to the different scales of outliers in each layer, for example, in the MLP layer, the outliers in the activations were much bigger than in the rest of the layers that were much more uniform. So applying SmoothQuant on those layers actually worsened the model. Therefore, in method 3, by only applying this SmoothQuant to the layer with the biggest outliers, I was able to decrease the perplexity. And the alpha that worked best for me was 0.4, which basically means that approximately the outliers were transferred equally between the weights and the activations. Here are the rest of the perplexities that I found for this model. So for GPT too small, and the original perplexity was about 29.92. And for the GPT-2X large model, the perplexity was approximately 17.14. Once I quantized it using the weight 8A8 quantization method, the perplexity increased a bit. This was aligned with the research results they had in the original paper. So for the GPT-2 small model, it increased from 29.92 to 30. And for the extra large model, it increased from 17.38 to 17.42. It was not a large increase. And however, later when I tried applying weight 8 activation, 8 quantization with SmoothQuant, the perplexity actually increased a substantial amount. So it became approximately 200 for GPT-2 small, and with an alpha of 0.4, here I chose the minimum perplexity of the alphas, and I tested it on all the alphas available with an increment of 0.1. And the perplexity for the GPT-2 XL model was 2064. And what was interesting for this result is that the best alpha was actually 0. And so it was actually better to just basically normalize the weights than to actually transfer the outliers from the activations to the weights, which means that probably the GPT-2 model is not such a large model, and that the activation outliers are not as big as to prevent us from using regular int8 quantization methods. Thank you so much, and I'll open it up to the Q&A.